What makes exactly a U-turn or parking feel so comfortable? Let's take a real example. For a typical U-turn radius of 15 meters, a car traveling at 10 kilometers per hour needs only a small centripetal force, roughly 700 newtons. At such low forces, the slip angle generated by both front and rear tires is tiny, small enough that we can safely treat it as negligible. At low speeds, tires roll almost perfectly in the direction that they are pointed. That means there is not enough slip angles there. If slip angle concept is new to you, I have made a separate video explaining them. Please check it out. Even though tires behave perfectly at low speeds, engineer has still to make one crucial decision to decide how much each front wheel should turn. When a car enters a turn, the inner wheel follows a smaller circle and the outer wheel follows a larger one. So the natural question is, how much should each wheel actually turn? Should both the wheels turn by the same angle? Or should the inner wheel turn a little more? Or is it the outer wheel that should turn more instead? So, which of these choices is correct for a low speed turn? To answer that, we must understand the fundamental law of steering. When a car moves straight, both front wheels are parallel. If you extend their axes, they meet at a point infinitely far away. When both wheels steer by the same angle, their axes never meet. Without a common instantaneous center of rotation, each wheel tries to follow a different circular path. Since the wheels are rigidly connected, the car ends up following a compromised path. The tires twist and deform to correct the conflict between the two desired paths. The deformation appears as lateral scrub. If the outer wheel turns more than the inner, the conflict becomes even worse. The axes move farther apart and the scrub forces increase significantly. When the inner wheel turns slightly more than the outer, their axes finally meet at a single point. This point is the instantaneous center of rotation. With a valid ICR, both tires trace their circular paths cleanly with almost no scrub. Pure rolling means the vehicle rotates about a common instantaneous center with a yaw at omega. Each tire's linear speed depends entirely on how far it is from that center. Look at the velocity vectors. The outer tires travel a bigger circle, so they must move faster than the inner tires. This difference in linear speed is exactly what the relation V is equal to R omega captures. To turn the tires, we need a steering mechanism. Each front wheel pivots around a kingpin, and a small steering arm lets us rotate it. When we add the second wheel and connect both arms with a tie rod, moving the tie rod makes both wheels steer together. The simple four-bar linkage forms the foundation of every steering system. When the steering arms are placed at 90 degrees to the axle, the tie rod pulls both arms equally, so both wheels turn by the same angle. That's parallel steering. For pure rolling, the inner wheel must turn slightly more. Tilting the steering arms inward creates a trapezoidal layout, and now the tie rod pulls the inner arm through a larger arc. This gives inner greater than outer. The geometric arrangement patented in 1818 by Rudolf Ackermann. By applying simple trigonometry to this geometry, we can relate the inner and outer angles needed for pure rolling. The cotangent of the outer angle minus the cotangent of the inner angle must equal the kingpin track width divided by the wheelbase. Here is how the inner and outer wheel angles compare. The straight line represents parallel steering, where both wheels turn equally. The curved line shows the angles required for pure rolling. Notice how both lines are almost identical at small steering angles, but the difference grows rapidly as the inner wheel angle increases. That's why inner greater steering becomes essential for tight, low speed turns to reduce tire wear. We have been discussing the steering geometry and pure rolling for low speed turning. Earlier in the video, we made a reasonable assumption that slip angles are negligible for a low speed turning event. But as speed increases, the lateral force required to turn rises sharply, and tires develop larger slip angles to generate that force. At high speeds, slip angles are no longer small corrections. They dominate and determine how actually a car turns. In reality, tires generate lateral force through slip angles, not through geometric pointing. So at high speeds, the effective steering angle shifts away from pure Ackermann. Tire stiffness, slip angle characteristics, and load transfer all influence how much deviation from pure Ackermann is actually optimal. To conclude our discussion on how a car really turns, we must understand high speed cornering. Slip angle balance, understeer, oversteer, and load transfer completely reshapes the turning behavior. We will explore all of that in the next video. If you find this content useful, please do consider subscribing. Thank you for watching.